Welcome, ladies and gentlemen, to your MN20 notes, where we're going to apply triangle sum properties from section 4.1 in our textbook. The goal here today is that we would like to classify triangles by both their lengths of their sides and also by their angle measures. Um, to start with the sides, classifying triangles by the sides, we have three different categories. We have either a scalene triangle, isosceles triangle, and equilateral triangle. While this is a review, it's a good review in case you have forgotten some of these words. The other thing I'm going to mention before I get into this note guide much more is that on page 217 in your textbook is a table that looks very similar to this note guide with maybe just a little bit more information if you need to look at that as a reference. But a scalene triangle has no congruent sides. An isosceles triangle has two congruent sides, and an equilateral triangle has three congruent sides. The angles, if you classify triangles by their angles, you have an acute triangle, which means that you have three acute angles. You have a right triangle, which means that you have one right angle and the other two are acute angles. You have an obtuse triangle. This angle right here is your obtuse angle. The other two are acute, but in an obtuse triangle, as long as you have one obtuse angle, that constitutes an obtuse triangle. An equilateral triangle, or equiangular triangle means that you have three congruent triangles. Now they're all acute, and if you break it down into 180 divided by 3, that means that each of these angles are going to equal 60 degrees. And that is the definition of an equiangular triangle. Just to mention it at this point, I do want to say that if you have an equilateral triangle and an equiangular triangle, you actually, by default, if you have an equilateral, you'll have an equiangular and vice versa because we know that the sides reflect the angle measures and vice versa. But if you have this kind of situation, you can also call it a regular triangle. A regular triangle means you have equal sides and equal angles. A regular quadrilateral would be a square because you have equal sides, equal angles. If you have a regular pentagon, that means you have all equal sides and all equal interior angles. Just kind of throwing that out there for later on in the curriculum. But here we have in example 1, it says classify the triangle shape of the shuffleboard scoring area in the diagram by its sides and by measuring its angles. The triangle, and I'm looking down here, it says, I want you to notice in this figure that we have two equal lengths of a triangle, which then, since we have a pair of congruent sides, it is going to be an isosceles. And by measuring the angles, and this is what we're going to be doing here, I'm going to try very hard with my protractor. I don't know if I can get her to work. Let me try that again. Yeah, it's not going to work. I would like you to try measuring it, and I'm going to say this. With a protractor, I know that you've seen them many, many, many years, but if as you're measuring with your protractor you're having any issues, please let me know. It takes me very little to show you again or review for you how to use a protractor. I will tell you that this angle right there is approximately 72 degrees. Anywhere really from 70 to 72 degrees is fine. If you measure this, it's also 72 degrees, not only if you measure it, but also because you have an isosceles triangle, so your base angles here are going to equal or be congruent. This, in turn, then, is going to be 36 degrees. And remember, the sum of the three angles in a triangle equal 180 degrees. So this space, it's going to be 72 degrees, 72 degrees, and 36 degrees. So down here it says we have it, so it's talking about a triangle. It is an acute because all the angles are less than 90 degrees, and it's an isosceles triangle. So that is how you classify. You classify both by its angles and by its sides. Now, if you by any said isosceles acute, that clearly is the same idea. Okay, now going on to the back, This is getting a little bit more into the guts of the math. It says in example 2, classify triangle RST by its sides, then determine if the triangle is a right obtuse or acute triangle. So the first thing we have to do is find the side lengths. In order to find the side lengths, and we're given coordinate points here, we're going to have to find this length, let's say to start with. You're going to be using that distance formula that we saw in Unit 2. So the distance formula of RS, and that's length RS. I'm going to write the formula here as a reminder. I'm also going to let you know that that's as a review in your MN8 notes, if I'm not mistaken. It's either MN7 or MN8. I'm pretty sure it's 8. But the formula goes a little something like this. You're taking the difference of your x coordinates, squaring those, and adding that to the difference in your y coordinates squared. And then after you find that sum, you take the square root of that. Now I'm going to go through this first one. So I'm going to show you how to find the length of RS using the distance formula, and then you'll be in charge of finding the other two lengths using the distance formula, since it is definitely a review. Since this is our xy coordinate here, our xy coordinate here, we're going to find the difference in our x coordinates. So I'm going to go 5 minus negative 3 quantity squared, plus I'm going to find the difference in my y coordinates. So 2 minus 3 quantity squared. So if I find the difference here, 5 minus negative 3, that's just like 5 plus 3, so we end up with 8 squared plus 2 minus 3 is a negative 1, and that's quantity squared. We have the square root of 64, 8 squared is 64, plus negative 1 squared, which is 1, and we end up with the square root of 65. So right here we have square root of 65. At this point, you're going to want to pause this video and find the length of the other two sides, and make sure you show your organized work. I'll check it tomorrow, and then start that video again and check it with my answer to verify that you're getting the right lengths. Welcome back. I did forget to mention that we are leaving them in square root form, these lengths, for a very, very specific reason. It actually makes things a lot easier when we go on to step number 2. But looking at these two lengths that you found on your own, you should have got, for RT, you should have found the length of square root of 52. For TS, you should have found the length of square root of 13. If you look at this point, the longest side is going to be that square root of 65. If you actually found the decimal approximation for that, it's 8.1. But again, it's easier leaving it in square root form. So the square root of 65 is going to be your hypotenuse because it's your longest side length, and then the square root of 52 and square root of 13 are your leg lengths. So looking at this, you have to decide whether this is a scalene, isosceles, or equilateral triangle. And since none of the lengths are congruent, we're going to classify it as a scalene triangle. Now this other space is determining how to classify it using its angles. So now we're going to use a good old technique that we used in Unit 3, which is the Pythagorean theorem converse, to find whether or not it is an acute, obtuse, or right triangle. And again, this is back from, I'm going to say this is MN15 as a review if you need a little bit more, but I have a feeling we've done it many times. You'll recognize this very quickly. It's a squared plus b squared, but we don't know if it's equal to, greater than, or less than c squared. We're going to put our lengths into the converse, and this is right where I said it's much easier leaving the lengths as square roots. Because when we do this now, the square root of 52, and when you square that, the square and square root, the square root and square undo each other, which means that you do just get 52 left. Plus, square root of 13 squared is going to be 13, and we don't know what's happening here yet with this, but square root of 65, square root of 65. So we end up with 65 is equal to 65. And we know that if the Pythagorean theorem converse is equal, or we find that when you fill in your legs and your hypotenuse it equals, you have a right triangle. If it were greater than, it would be an acute triangle. If it were less than, it would be an obtuse triangle. And again, if you need a review of that, it's MN15. Coming down here, so just again, to take a step back actually, so this is a big problem. We found the lengths of all three sides using the distance formula from Unit 2, and then we found whether or not it's obtuse, acute, or right using the Pythagorean theorem from Unit 3. There's not a lot of new skills here, but it's definitely using our tools from the past to determine or to classify this triangle by its sides and its angles. So here we have a theorem, it's called the triangle sum theorem, and really you guys already very much know this. Angle A, the measure of angle B, plus the measure of angle C, when you add all those up, it does give you 180 degrees. And you're probably rolling your eyes at me, but I do want to make sure you realize it is a theorem, a very proven theorem. This next theorem is a biggie. People sometimes forget this, but it's called the exterior angle theorem, which means, or which states that if you have angle 1 out here, and you add that length or the area, excuse me, the that angle measure is going to be the same as if you were to add measure of angle A plus the measure of angle B. Now, at first it looks a little obscure, but let me just kind of explain this. If I were to number these angles, the rest of the angles, let's say this is 2, this is 3, this is 4. We know that by the theorem above that angle 3 plus angle 4 plus angle 2 is equal to 180 degrees. That's a given, right? We also know from unit 1 that angle 2 plus angle 1 creates a straight angle, and that equals 180 degrees. Really, the only thing that we have overlapping is this angle 2 right here. So if we take out that angle 2, since these two equal 180 degrees, and they do, in fact, equal each other, if you want to look at it that way. It's called the chain rule, but you can also just use logic to think about how that works out. But I'm just letting you know this is a biggie. How do we use it? Well, that's kind of what I'm going to show you here in example 3. So we are trying to find the measure of DCB. So we know that DCB, according to the theorem we just talked about, the exterior angle theorem. Now notice this is an exterior angle, it's outside that triangle. Angle DCB is going to equal the measure of angle A plus the measure of angle B. DCB can be represented by 3x minus 9. The measure of angle A can be represented by x, and the measure of angle B can be represented by 73. And now, very much like what we did a lot of in Unit 2, is once we have an equation set up to represent our situation, we solve it. So we subtract x. We have 2x minus 9 equals 73. We add our 9 to both sides. We have 2x equals, what is this, 82. And then we divide out by 2. We have x is equal to 41. So this is a very important point. This is the unknown value, which is 41. To find the actual measure of angle DCB, you need to remember though that 41 degrees is clearly not the answer to the question. The question is what's the measure of angle DCB, which is represented by 3 times the x minus 9. So we want to put that unknown value, that 41 that we solved for, into the expression and do a little bit of math here. We got 3 times 41, and then we subtract 9 from it. If I'm not mistaken, that's going to be 114 degrees. So this right here is 114 degrees. Now, what you're probably saying to yourself, well, if I use the exterior angle theorem, couldn't I have just said, well, I can see that this here is 41 degrees, and this angle B is 73 degrees, so can't I just go 73 degrees plus 41 degrees gives me that angle DCB? And the big old answer is yes, it is. So if you saw that, good for you. So I'm just saying the angle of measure of DCB, angle DCB is 114 degrees. So really today is all about classifying angles by its sides and its angles, and then from there, looking at this exterior angle theorem. Thanks for joining me.